was.
Okay.
The
Yeah.
There's no
PTC, PTZ. Yeah.
Yeah, I don't have any organometallic complexes functionalized. That was all Pung, and I don't think Pung has any data that I can access
Yes, he didn't.
to give him.
Yeah, I know. But in any
If
case...
he wants, I can make some.
Well, I think John can make it by himself, can you?
Yeah,
Well,
yeah, no, that's not an issue.
What I just want to be sure that you have the quantum dot. So what I ask you to do is, can you prepare the file in a Word, in a VASP kind of format?
Yeah, as you say, I mean, so I have, what I got from Levi were 4 different structures.
But Levi, he gave you just XYZ coordinates, right?
Yeah, and I've already built them into VASP files.
But you
and
can,
I have some of them.
Yeah, please, because you will have to run it in a VASP anyway. So please make the file, and even if you didn't optimize, can you send it to me, because I will send it to Andre and he will do his things with it.
Yeah,
and also
no, that's fine.
Would be also good to put the ruthenium complex. Maybe if you can create it as another additional structure.
Yep.
And these things that you want John to send you, you want the optimized structure, correct?
Well, did you optimize it?
The ones that I had, I believe I optimized it.
But did you optimize in VASP? Oops.
No, in Gaussian.
Okay.
Right.
Well,
So
I have some of them running in VASP right now.
Yeah, we will switch it to VASP anyway, so he has to re-optimize it probably at some point. What's going on?
Okay.
What we are looking on?
You're looking on a microphone.
Aha. Many of them? Okay. I just was waiting for you.
I'm done.
Who is the first? John is finishing?
John, would you like to finish something about your literature review?
Yeah, that's fine.
You're not very enthusiastic about it.
No, actually, I do. I have some questions, and some things that I wanna go through. So, I am actually kind of excited to do this.
But is it the same slides, or did you modify them?
So I have some different slides than what you guys had in front of you, and so do you see the screen right now?
Yeah, we see you and we see the screen. It really works perfectly.
Okay, and so right now it should be a 2015 slide.
Now?
No, right now we do not see.
Black.
Now we see you only, not. Return to one step back, please.
Before we saw it, but now it's disappeared.
Okay, then let me try this. All right, do you see my whole screen now?
Yes, very colorful.
Okay.
And now we see your
now
slides.
We see it, but yeah.
All right, so we're on a slide of 2015.
Perfect.
We are on slide number 12 that presents a paper from year 2015. Yes.
Okay. So, so this is probably where I'll start then. One of the main things I found in going through some of the newer literature from 2015 going forward was looking at the type of linker group that gets used for binding the ligand to the quantum dot surface. And so a number of the studies that have been done in the past were focusing on carboxyl groups as the primary linker between a quantum dot and ruthenium type complexes. And so this was a study done in 2015 by in Filippo's group. So they were just looking at cadselenide quantum dots and looking at the difference between carboxyl linkers in this QD1 and this dithiocarbamate type sulfur linking group in QD2. And so moving forward in time in the rest of the papers, you'll see that people are moving more towards this dithiocarbamate type linker or some type of thiol linker. So these sulfonate groups.
Before you go, I just want to ask a question. So in both cases, the ligands which are used, they are ionic ligands, right? So they have a negative charge, right?
Mm-hmm.
And then the quantum dot, is it having the same number of cadmiums as seleniums? The quantum dot by itself, is it neutral? or
I
they have more
believe
cadmiums or more seleniums? Looking like on the structure, looks like it's kind of the same. And I'm just confused because I'm not sure how they balance the charge, because if they have so many, how many, 21, or how many ligands they have? If they have each of them negatively charged, so you're creating a huge charge on the surface through the ligands, which looks kind of not very realistic, right?
Mm-hmm.
And you can balance it somehow, either putting some positively charged ions somehow around on the surface, or you can balance it with positive cadmiums if you have more cadmium ions.
Right.
And then
I
less
thought this paper had non-stoichiometric quantum dots.
So they balance it through the cadmium, having more cadmium ions to balance the charge.
Okay.
Yeah, so there's 40 cadmium and 31 selenium.
Okay, makes sense. So the overall it's neutral system.
Okay. All right. And I'll double check that again, but thank you, Levi.
I looked at the paper.
Okay, perfect. So the main thing that they were highlighting was the different types of linker groups. And so what I wanted to show here was, so one of the density of states plots that they have in looking for the black line being the total density of states in both of the systems, the blue line being the density of states contributed by just the quantum dot itself. And then the red density of states line is what's contributed by the ligand groups that they have. And so quantum dot 1 has the carboxyl linkers. And so you can see that the valence band states close to -6 eV here are they're almost entirely contributed from the quantum dot itself. Whereas once you switch to this dithiocarbamate type linker, you can see that the red line labeled 2 comes up and plays a much larger role at the valence band edge. And so using this going forward is this paper in 2016 by Emily Weiss's group in looking at this type of fast hole transfer to this PTZ complex through 2 different types of linkers. And so
and again, I interrupt you. So Levi,
Yep.
This is the system which you were trying to model in the beginning, right? This is the ligands which
Correct.
you use? Okay.
Yes.
Yep, and this is the system with this PTC linker that I have running right now, at least in VASP for kind of a first look at things. And so in looking between these 2 types of linker groups with the sulfurs versus the oxygen, they found that there was a much faster hole transfer rate through the sulfur type groupings. And so it had nothing to do with bond distances, because with the oxygen type groups, it was actually closer. And so their main answer for description as to why they think this is going faster was basically saying, we think there's better coupling between the quantum dot and this linker with this dithiocarbamate type linker. But that was about the end of the description. They didn't really provide any other type of hypothesis on what type of chemical characterization within those type of linkers may be actually contributing to this type of increased coupling, leading to this ultra fast hole transfer. So I think that, using this as kind of a first test model, that may be something we can contribute, is actually giving the chemical characterization and what's specifically contributing to the increased coupling, leading to these types of fast hole transfer rates. And so then going forward, there was more implementation of these types of carbamate groups. And so here they were looking at these catselenide quantum dots that was in an aqueous solution. And I think being able to do aqueous chemistry is a big step, because it's, it's a very readily and common solvent for people to be able to use. But what they're describing here, and what Emily touched on a little bit before, is with these dithiocarbamate linkers, you're creating almost like a whole delocalization around the surface of the quantum dot itself. But what they were exploring here in this paper was what you're attaching to this type of carbamate linker is going to direct any type of further either collection of the whole or taking an electron onto the system. And so this type of aromatic group can be conjugated with the diethylcarbamate linker groups, and that allows a further transfer of this whole to something in the solution that can come in and extract the whole from the surface link. And so, in Emily's paper here, you can see the same thing. They use this planar aromatic group connected to the linker and use that conjugation to pull it all the way out to a terminal group that they were interested in. And so, I guess depending on how we want to direct it, which if we're looking for photooxidation of some other products, this can be a good step for looking at this type of linker plus some conjugation leading into, either some type of ruthenium or iridium, some type of metal organic complex, if we want to try and utilize a larger grouping on the side of it. And so something I'd also mentioned kind of at the end last time was this discussion of a nickel catalyst being added into the quantum dot system to accommodate electron transfer from the quantum dot conduction band, allowing this charge separation between the electron and hole, giving it more of a longer-lived charge-separated lifetime. And so with these two different papers and discussion of these nickel co-catalysts, they were looking at the difference. Well, so this JPCC paper, they have it designated quantum dot 1 and quantum dot 2 within the paper, and basically the only difference was how long they let the reaction go before they quenched it. So we're just looking at different sized quantum dots, and so with the reduction of quantum dot size, the surface chemistry becomes more dependent on the atomic species, and different surface defects are more prominent. And so,
is it possible? Can I interrupt you?
Yeah.
So you, I'm getting backwards authorization. So in your no, please keep the slide. The slide on. You will not see us. We have focused camera on the screen.
You can go and ask questions in front.
And then everyone needs to go there.
So everyone goes and questions there.
It's a quick for large question. I will come there. So under the 2017, you have graphical table of contents or whatever, figure 9, and at the upper right you have nickel 2 plus ion.
Yes.
It shows electronic state, but what is the morphology? Is it like ion doped into quantum dot, or it is coordinated to some ligands? What is the morphology of this nickel?
Yep. So I was just going to mention that. So the nickel itself is actually a physisorbed nickel ion that replaces a lead defect. And so that's also something I would like to explore in this project is swapping out one of the cadmium atoms for a nickel atom and taking a look at what's going on.
But which quantum dot do they use?
This one is with the cad selenide.
It's cad selenide with nickel
doping,
or whatever they call it.
Yep.
Thank you.
Yeah, and so that's why when they were, I think the diameter of the smallest, like this quantum dot 1, was like 1.8 nanometers. So I mean, it's still pushing close to maybe the limit for what we want to do. But yeah, with the reduction of the size, increase of the effect of the different defects within the surface. And so the the nickel can come in, populate a surface or a physisorb to a surface defect site from the cadmium, and then enhance this type of electron transfer to the nickel. And so their premise in their study was by being able to control the different types of trap states available within the system, you can enhance the type of hole extraction to some other organic piece. In this case, they used the ascorbic acid. And so I talked briefly last time about this top left image. So, you know, option 6 or step 6 is this hole transfer from the valence band of the quantum dot to this ascorbic acid. So just grabbing the hole out of the quantum dot. But the second step that they have here of this hole trapping due to some of these surface states and stuff is what they're saying is being a huge promoter or benefiting the overall system. And so the paper listed in the bottom left is, again, another one I mentioned the other day. They try to make use of the same type of system of adding this type of nickel dopant, well, I guess not dopant, but this nickel co-catalyst into the system to enhance other types of photooxidation reactions. And then another paper that I had looked at was just something that we had kind of touched on and something you had done, Professor Kalina, about looking at adding or, you know, dictating what type of charge additional functional groups add to ruthenium complexes and being more of an electron donating or withdrawing type of system where you have the change between electron donating and withdrawing affecting where additional energy states are going to be localized relative to the energy levels of the quantum dot. So here, like this 4MP is a type of electron donating group, and so it's going to have a better option to pull or be more of a hole transfer material compared to this phenyl with a nitro group on it. And then this was another paper, not exactly, you know, what we're going to want to look at specifically, but I thought could be interesting to look at was the fact that they're using.
John, the previous paper was experimental or it's computations? What is it? Kind of hard to say just looking on a graphical abstract.
Oh, sure. So this was an experimental paper that they had done doing this with these type.
They experimentally measure, what exactly they measure? They measure the charge transfer through the fast probe spectroscopy?
Yes, I believe so. I'm trying to pull back on what that was. Let me see if I made any notes on this. Just that it was electron donating. No, but I believe that's what they were doing. And then, yeah, so with this one, they were using cadmium quantum dots, photoexciting them, and then having this type of linker group connecting to another nickel oxide quantum dot, but also having this cobalt type metal organic complex nearby, also linked to the nickel, and being able to separate the two charges that way. And so I don't know if this is going to be something that, you know, we could consider analogous to having some type of organic linker group, this style type linker group, and then, you know, attaching it to another larger metal organic complex that could take, you know, have some of the properties of the nickel oxide, at least and directionally with energy levels. So that was just something I was thinking about whenever I read through this paper.
The charge transfer, what exactly is the charge transfer going to, from? So the quantum dot is excited or the complex is excited? How exactly it works?
So in this paper, the quantum dot was excited, and then there was a charge transfer of the hole through this bicarbonate linker again, or carbonate linker to the nickel oxide, while there was this type of other electron charge transfer to this cobalt organometallic complex that also happens to be like a second ligand on the nickel oxide surface.
So the hole is created on nickel oxide due to the transfer from quantum dot? No?
Well, yeah.
Well,
so the
hole transfer from the quantum dot to nickel oxide.
Yes.
And then means nickel oxide is losing the electron.
Mm-hmm.
And then you're saying that there is an electron transfer also from the dye, I mean from the metal organic complex, kind of compensating this hole in a nickel oxide. So that's kind of making your nickel oxide be neutral and you creating the charge on a, if it's losing the electron, so it's a positive charge on a cobalt, more positive than it was before. Let's say if it was 2+, now it's 3+. And cobalt,
Right.
is it 2+, or what is the oxidation
Yep.
state?
So the schematic on the left in so panel B there, they show a cartoon of the image. So there's some initial excitation up to a conduction band, and it goes into a cobalt 2,1 and then to a cobalt 3,2. So I think depending on just some of the very specifics of the coordination around the cobalt, it's just gaining one electron and going from 1 to 2 or 2 to 3, that type of thing. But yeah, that one I was just thinking more a little bit bigger picture and to consider if that was something, just thinking directionally of how to align the energies. Yep. And then the last thing, which I don't know if, I don't know how much time we want to put into this, but these were two newer papers, I guess, from 2017, both in looking at generation of carbon-carbon bonds through photocatalysis with these type of lead selenide quantum dots. And so I pulled the paragraph that's on the left from the conclusions of the second paper. And the only thing I really wanted to highlight out of this was that, they're suggesting that these cad selenide quantum dots can replace ruthenium and iridium complexes that are, most often used for photoredox chemistry. And they want, they propose one of the issues is how can we adjust the composition and the surface chemistry, the ligand chemistry of the quantum dots, to enhance this even more. So I think that's also another area where if we start looking into specific solvent effects and potentially other types of organic molecules around what we think are really good photo oxidation centers, driving them back towards maybe implementing some of that and looking for specific chemical reactions. At least in a larger picture, it seems like there's a number of people that are very interested in this. And then this one, I was going to take this one out. This was just looking at how having deep protonated types of molecules, so solvent effects, can wedge their way in between surface ligands on top of a quantum dot, can create a type of charge transfer, deprotonation and protonation of one of the solvents and the ligand itself, and how they're positioned around the surface of the quantum dot can lead to different rates of electron transfer. But I think that might be a little more towards the future, because I'd like to start with some of the smaller models just so we get them going through and getting some of the results. So I showed you these two slides the other time. So what I'm looking more specifically in are a lot of the papers that I've been finding and reading have been mostly cadmium based. So cad selenide, some of the things that you had looked at looking at electronic structure are the cad selenide with a black dye, primarily with carboxylate linkers. But I'm still trying to find something that has like a dithiocarbamate linker, just because.
But again, for these complexes, it's probably not a very hard deal to change the linkages on a bipyridine or whatever ligands. And again, as a model, we can just change carboxylic group to phosphate or to the whatever sialate group. Also, if we go to the, actually we just submitted the paper, which was written by my student last year. We submitted it finally. So he was doing the black dye, which has either, how's it called? Either cyanide ligands, right?
Mm-hmm.
And he was showing that you can attach, like it's not the same linkage as, let's say, in the Weiss group where you have 2 sulfur, right? Here it's just single sulfur, but you can attach it not through the carboxylic group, but through the sulfur, and the electronic structure is changing, the alignment of ligand versus the quantum dot is changing, the binding energy is weaker comparing to the carboxylic groups, but the electronic couplings he calculated through the how it calls, through the not reduced DFT, confined
DFT?
no confined DFT, how it calls?
Constrained.
Constrained DFT. So he calculated it through the constrained DFT when you really hold in charge on a quantum dot or whatever, positive and negative on a die or backward. So he was calculating it, showing that couplings really much larger, electronic couplings, much larger for cases when it's attached to this sulfur group.
Yep.
So we kind of already know that, yeah, we have not exactly the same things as was done, let's say, on the Weiss group, but probably even if we make a model and just change this linkage group on a molecule, it probably would be good enough, even if you can find it in experiment. I think it's really, it will probably take some knowledge on organic chemistry, but they probably can functionalize the ligands with whatever the groups, and probably it's not a big deal.
Yeah, well, and that's kind of what I was thinking. Yeah, because I've been trying to find actual chemical structures for them, but yeah, it's easy to swap the linker groups. And in some of the papers too that I've been reading, there's a discussion between, so this type of dicarbonate with, 2 sulfur atoms versus just a single carbonate versus like a thiol group. And so people were wanting to tend away towards thiols. There were a couple comments. I need to go back and go through some more of the references to why they wanted to do that. But it definitely seems like sulfur is the better linking group, just because of the delocalization of some of the orbitals that you can get around the quantum dot surface. And then, so also with the CAD selenide, so in the paper that used the conjugated linker, that's the AMBZ DTC. So I think, it's very similar to the PTC PTZ type linker, where they used, a planar aromatic to conjugate with the linker group itself to facilitate more of the whole transport. So being able to take a look at some of those types of planar aromatics attached to these linkers to some of these larger groups is something I'm interested in. And then also looking at these nickel co-catalyst, or the physisorb nickel on the surface and the cadmium structure, and they use 3-mercaptopropionic acid, which is just another type of thiol group. So again, it's just attached through a sulfur group. It's just a small organic molecule. So that might be a good place to start. But we could also add more complex ligands on top of that if we choose to. And so, playing around with some of the things, some of the parameters I have listed, some groups, they're showing multiple different different types of ligands on the surface, and how you can have directional transport between different charge carriers. Where on the, or what quantum dot surface is the ligand actually attached to? And then, maybe later down the road, we can look at trying to implement some solvent effects, just because that's going to, I think, play a little bit more of an important role when you're looking at some of these papers that are in aqueous solutions. Some of them are done purely in organic solvents. And so that can play, a significant role in what's all available electronically within the system. So this is kind of the direction, focusing mainly on some of the cadmium type systems, but I know also we can easily do some of the lead systems as well, but this is the direction I'm thinking for right now.
Hey, John?
Yes.
Your 4th bullet point, where you're saying you're searching for organometallic complexes with the DTC linker.
Mm-hmm.
From what I know about how they synthesize, like PTC, PTZ, they bubble through carbon disulfide gas through like at a mean derivative of the conjugated system, and that forms the compound by proton exchange. And I and Svetlana and another a collaborator, we worked on a paper showing that that is very unstable, because you have to do like for quantum dots at least, you have to do like a ligand exchange. So it may be difficult if you just go straight with, if you try and find DTC organometallic complexes, because they might not be able to do that type of reaction where they bubble a gas through to form the complex.
Okay. Yeah, because what I was finding when I was going through and actually trying to find some of the complexes is when they have, DTC around different types of metal ions, it's almost like a self-assembly type system, but the sulfur groups are actually focused around the metal ion and enclosing it instead of being the actual linker groups. And so that was, I'll have to take a look at that. Yeah, it could be that's just hard to do.
Like the nitrogen-carbon bond, that is very weak, because if you get a proton transfer to the nitrogen, then the nitrogen can do an electron transfer and break that bond. And depending on your solvent, it can be like the half-life is like less than an hour. Okay. So it's not stable, which may be another reason why they don't have many with that linker group.
Okay.
Which may make it easier to do the thiol groups than the DTC. And that might be one reason why they're trying to go with thiol instead of the dithiocarbamate.
Okay, thank you, Levi.
Yep.
But yeah, so that's.
But you can also. I don't think there were a lot of efforts on a quantum dot interaction, but there is for Grätzel cells the attachment through the phosphate group, right? So when you have two phosphor groups, which can attach in the same way as a carboxylic group, but through the phosphor group. So this is where they also studied it a lot, and I think they have probably better electron transfers through the carboxylate groups rather than through the phosphate group. But the difference is not probably very strong. Like you can see, for sure, you can find a lot of papers if you really look on like titanium dioxide surface with metal organic complexes, ruthenium complexes. So yeah, mostly it's ruthenium complexes, but maybe there are other complexes as well. And you probably will find it's linked through the, again, most of them linked through the carboxylic group, but there are also where some comparisons, there are many work were done for phosphate groups. And for quantum dots, phosphate ligands, right? So phosphor-type ligands, like we call them TOPA, this is with oxides, right? And TOP when you have just phosphor groups attached. So they're also very common, and initially when they synthesized quantum dots, they were using the phosphate or phosphor groups for attachment. So which means if we have a ligand with phosphate group, it probably will be easily attached to the surface, and I don't know, maybe it will be working better than carboxylic group, or maybe it will be the same, but this is also, looks like we don't have experimental evidences, but this is very realistic system, and if we cannot get something with with two sulfur groups, then you can try phosphates.
Okay. No, I'll definitely go through and look at that then. Okay.
Is it your last slide?
Yeah, that was my last slide.
Oh, okay. Any other questions? Maybe. Should we applaud?
Yes, let's applaud.
So good. Oh, and can you send it looks like you have updated your presentation comparing to the
Yes.
last one. So
Would you mind share?
Yeah, would you please then send us the most recent version? Because some
Yeah,
papers I would definitely would like to have it for myself to
Okay.
use it later
Yeah.
for the literature review and so on.
Yep. Yeah, I'll turn that into a PDF, and then I'll just attach a bunch of the papers with it if you want those. That way you don't have to search for them.
It's okay. You just send your slides.
Okay.
In PDF or PowerPoint, doesn't matter.
Okay.
Good. So we are ready.
And let's applaud him once again. Oh, and let's applaud to John for the third time. The paper based on his research in Los Alamos is accepted for publication in prestigious journal of ACS Energy Letters.
Hurrah!
Congratulations to John.
And
How long
you're
did it
also an
take you?
author on it, so.
How long did it take you to write to finalize everything on this paper? When did you start working on it?
Well, so that one was written by a postdoc that's there now, Ling Zhang,
But
I think is their name.
But they use your data there, right? Otherwise,
Mm-hmm.
you have your name there as well. So my question is like, when you start working on this? Like 3 years
When
ago?
did I? So the data that we used for it was done like the last month I was there. So about a year ago, year and a half ago.
But you started working on this project, I think, about 3 years ago.
Mm-hmm.
Yeah, so sometimes I'm just kind of giving you some idea. Sometimes it really takes a lot of time to finalize a paper. Like you start getting your data, but it's really a process.
Yeah.
Okay, so we ready for Levi? Are you ready to present?
Yep. Can you see it?
No, we
No.
can see only you.
And John looks
I'm-
bigger on the screen. Okay, now we see.
Yeah, but we still have, I don't know, is it possible to switch? Now we have a big John and small Levi.
How about now? If I talk, do I make myself
Oh,
bigger?
now it's better. Yeah, now John is small.
Perfect.
But do you see the blue background?
And black, yes.
Like, do you see my slides?
We do see your slides.
Okay. So today I'm going to talk about understanding the phonon-mediated exciton relaxation in lead caucagenide, cadmium caucagenide core shell quantum dots. So I'd first like to start out with what are core shell quantum dots. And in this case, we are going to be looking at a crystalline core and a quasi-crystalline shell. In experiment, we're looking at an amorphous shell. In experiment, theirs is quasi-crystalline. And if you look at the figure on the right, where it has the lead solenoid and then it has two other images, the way that they make core shell structures is they originally start out with like a 4 nanometer radius of quantum dot, and then they do cation exchange. So they heat up the system to over 130 degrees C with cadmium precursors on the outside, and this heat, the heating process allows for lead vacancies, which then allow the cadmium to permeate to get inside to make the giant core shell structures. And if you see in the first arrow that says 100 degrees, if they don't go past 100 degrees, the shell is it will saturate and won't go any further in. So they have to heat it up kind of extreme. And this architecture of quantum dots is kind of unique, where if you look at the left figure, it has like effective mass approximation orbitals, where you have the conduction band, the conduction band that is spread over virtually the entire quantum dot. And then you see states that are higher in energy compared to the pink states. and those are centered on the core of the quantum dot. And these states are very unique because if you excite higher than them, these states tend to slow down the relaxation so that you can get a dual emitter. So if you see the green light, the green arrow, that is visible light being emitted, and then the red is ultraviolet, infrared, which is very important. And if we take these and we ask why are we studying these type of quantum dots, they are relatively easy to synthesize. You just take your major quantum dot with the lead caucasianide and you just put in a solution of cadmium and you heat it to make the quantum dot that's core shell. And the precursors and solvents are pretty abundant. Experimentally, quantum dots blink, and blinking means that they have emissive properties at some point, and after some time, they become optically inactive, and then that cycle continues. But if you go to giant core shell structures, that blinking will be reduced, and it will be, the on time will be very long. Additionally, since we are confining the holes to the core, Coulombic attraction is enhanced, which can result in higher multi-exciton generation in these systems. And additionally to the Coulombic attraction, if we think about what other processes compete against multi-exciton generation, we need to think about the relaxation of the electron and hole. And in these structures, you can modify the relaxation due to chemical composition. And additionally, since there is the, if we look back at the left figure, since there is a spatial confinement between the higher holes and the cooler holes, that spatial difference allows for slower relaxation, which is another plus for these systems. So let's talk about what is known, and a lot of this I've already kind of alluded to, but let's go over it nice and concrete. So due to the fact that we have these spatial confinement in the orbitals, the relaxation from, in this case, the 2SH to the 1SH is relatively slow, which allows for radiative relaxation and emitting visible light. And if the hole can relax down to the band edge, then it can do infrared light going from cadmium selenide, those two. And this very slow relaxation from the 2SH will enhance the multi-exciton generation due to the fact that we have additional excitonic energy. Additionally, what we know from the effective mass approximation calculations is if we take the ratio of the core, the shell to core, as that parameter rho gets larger, the spatial confinement is enhanced, which is shown in the figure B, where originally the core localization is near to 100%. And as the shell gets bigger and bigger, the localization on the core drops. In our systems, we never get to really big rho because we can only simulate such big, so big quantum dots. Additionally,
wait. Can I interrupt you?
Yes.
One slide back. On the one slide forward. One forward.
This one?
No.
This one?
Yeah, this one. On the panel A,
Yes.
what is x-axis?
X is rho.
What?
And it kind of got cut out.
Is it coordinate or momentum?
So H here is the parameter of how thick the shell is.
Okay. Okay, good. Thank you.
And these quantum dots, if I remember correctly, are 4 nanometers in diameter, which then the far right would mean that the core is only 1 nanometer.
Good.
So if we, the large shell also increases the lifetime. If you look at panel D, you see black, which is no shell, to magenta, which is a very large shell. The lifetime of the state gets longer and longer with the delay, which means that the hole is taking longer to get to the state that they emit at. What else we know about this is the lead cacadronide, cadmium cacadronide has shown to increase the rate of carrier multiplication. This could be done through either Coulombic attraction between the excited charge carriers and the non-excited charge carriers, which then excite, or it could be due to the fact that if we increase the rate, if we decrease the rate of cooling of the carriers, the excess energy is around longer, so carrier multiplication has less chance, it has more chance to occur because there's more energy for longer. And in this paper, they were talking about phonon-mediated cooling, where if you compute the cooling rate, it is directly proportional to the phonon frequency and inversely proportional to the phonon lifetime, which means if you increase the frequency, the rate will also increase, and if you increase the lifetime, the rate would decrease, which in the work that I'm doing, I think that the phonon frequency of the quantum dots will be a very important parameter to look at, because we're looking at sulfur and selenium, which they have different frequencies, and the frequencies can kind of go into the excited state dynamics, the rates that they occur. And the last thing is we know that reducing these systems reduce the carrier multiplication threshold, which I will explain in the next slide. So if we look here, the left side is the core shell structure. So if we excite from the shell, which is the bottom where you have the hole on the 2SH, up into the conduction band, we have excess energy, which is labeled EH, which can be used to excite a secondary electron hole pair. And this allows the energy of the exciton to be lower compared to like the visible onset, because the oscillator strength of exciting the core can be somewhat weak. So if you excite very optical states, you're exciting lower into the valence band, which allows for a lower threshold for your carrier multiplication compared to the non-core shell, because of the fact that you have to excite evenly into the conduction band and valence band, which does not allow for the cooling the carrier multiplication to be as efficient in the core shell structure. And this is just an example. This is just showing on A, you have the cooling of your electron, which is the red dot down, and that is competing with B, the carrier multiplication, which takes the excess excitonic energy from the electron and gives it to a hole in the conduction band, which then can excite up to the band edge in the valence band. So some open research questions are, does our system adequately describe the experimental setup? And the system that we're using is on the right, where I took out some of the atoms to show our core shell, where here we can see the lead, which is the black or gray, is in the interior, and then the cadmium is on the exterior. And from what I've seen, it is pretty decent. And here is the electronic properties, which we can see a subgap at about negative. Yes.
The play of the game is that you provide only introduction. You don't go to the results. And okay. I didn't get any idea how all the things which you discussed before about how important the carrier multiplication and all this kind of stuff, how exactly, like what exactly you are studying with your approach. How all the things which you discussed really connects to exactly the things which you will be discussing later in your paper.
Yes, so I guess the important thing to take away is if the phonons assist in the carrier relaxation, that is very bad for carrier multiplication, because the lifetime for carrier multiplication then has to be even faster compared to the fast rate of relaxation. So if we can slow down the phonon assisted cooling of the charge carriers, that will theoretically help increase the rate of carrier multiplication.
Okay. So?
Yes?
Yes, but still unclear what exactly then you do, because you're not calculating carrier multiplication.
Correct. So, one of the research questions
you are addressing. Again, when you write a literature, let me finish my sentence. When you write a literature report, because again, it's not just a presentation. All the things which you discussed, yeah, they're interesting, right? Great. But we're not just discussing the papers which you read. The thing which you have to present, right, is really should be focused on the part which will be reproduced, will be written later on in your introduction, right? And you were spending, I don't know, about 30 minutes, or how long you were talking already? Yeah, you were spending about 20 minutes for sure, talking about the carrier multiplication, again, how important it is to have this structure versus that structure, and so on, right? On the things which will be not really in your paper, not really in a subject of your paper. So if you really put in all this discussion into your first page, or how many pages you will spend for this discussion in your paper, the readers will be really very confused, because if you start with this, they expect that you should talk about carrier multiplication in these systems, and you are not, then definitely this is not your main point, right? Then it's completely unclear. If this is not your main point and you spent already 20 minutes on it, then what is your main point? I still didn't get it. I mean, I do, but I think others didn't.
So my main point is what chemical, what can we do to the quantum dot core shell structure to slow down the rates of relaxation of the electron hole?
What can you do to slow down the relaxation? Well,
Yes.
what actually, okay, great. If you put this, let's take it as a statement. What can we do to slow down the relaxation? So then, what exactly can you?
So we are looking at changing sulfur and selenium to cacagenides to see the effect that these two anions have on the relaxation rates.
Well, since you're just really considering two structures,
Yes.
I would say starting with the statement, what can we do to slow down relaxation, sounds a little bit strange. Because if you state it like this, then people expect that, oh, you will go through trying different shells, different cores, maybe putting different ligands on the surface. People really expect that you will be varying many things to figure out what the parameters would really have the largest impact. And you have only two parameters, actually two structures, cat sulfide, lead sulfide, cat sulfide, or lead selenide, cat selenide. So I would say this kind of statements is a little bit leading us to a different discussion. So probably you have to reorganize it or refocus it.
6.
Can you?
Cacagenides. So like 11. So
I can't hear you, Aaron.
oh,
You
let's
didn't
add
hear
a
me?
question. Well, why don't you ask Levi, see if he knows.
Oh, I'm sure he does. I didn't know what a cacagenide was. Or
So it is oxygen, sulfur, selenium, telluride. It's that family in the periodic table.
Okay.
So like a halide is like fluorine, bromide, iodide, and I forget the last one. It's just a row, a column in the periodic table.
Got it.
Okay, returning back to my question, actually, Paul.
Yes.
So can you clearly
Oh,
state
yes, I can see.
what exactly you are doing? Oh, you can change it, right? What exactly
What?
do you? I mean, who was changing it?
No.
Oh, this
Someone should-
I did.
Ah, okay, good. So what exactly can you do? Oh, not exactly can you do. Like again, starting with the saying that, oh, what we can do to slow down the relaxation sounds really not really applicable in your case because you really consider only two structures. So can you kind of make this main point, which is really important point in your introduction? So what exactly is the open questions there and how you're really addressing it? But it has to be addressed directly to the things which you are doing in a paper.
So could it be understanding the influence of sulfur and selenium on carrier relaxation?
Okay, so this is better. So you are really kind of making it more specific and just saying that you want to see how much the composition of your core shell structure affecting the relaxation rates. Can you hear me? It's freezing. What should we do? Can we do anything?
You can upload him.
But he can.
If you've been recording, he can listen how you were uploading.
Is he going to return back to us? Or can you disadvantage him probably? What if you
So
disadvantage?
I do have one question. And when Levi comes back, he can answer it as well. So, I mean, if you would constrict the size confinement even further, you could decrease the rates of relaxation for non-radiative mechanisms.
The answer is
But
no.
is he gonna?
The answer is
The
no.
answer is no.
Yes. This was the whole story in the beginning of 2000 forever when the slowing down the relaxation is called the phonon bottleneck, right? So you have go to the slow relaxation because the energy of phonons, the energy of vibrations, is much smaller than the energy between the electronic levels. So you have a mismatch, like this energy to jump from one electronic state to another is much larger comparing to the energy which can be given to the phonon. In this case, you need to give this energy to multiple phonons to match the energy, and any kind of multi-carriers or multi-phonon kind of processes is less probable than a single carrier. So which means it will be again slow and so on.
Right.
So that's
So-
why what you are saying, this was initial understanding that, oh, the smaller the quantum dot, the slower the relaxation should be.
I
But
lost connection for the last like 2 minutes.
yeah, we know, we noticed. But
Oh.
John asked the question which he addressed to you, and I started answering the question. But maybe you can now help me with it. So the question was: is it really true that if you reduce the size of the quantum dot, then you should slow down the relaxation?
Yes.
Okay.
No, the
So
answer is no.
But your states become larger split.
Yeah, they become larger split. And nonetheless,
Oh,
the electron phonon couplings is large
Yeah.
in the quantum dots, right? And here was a whole thing why this is happening, and there were several papers written just to this kind of question: why the phonon bottleneck is not observed in the quantum dots? And then in the small quantum dots, when you have really a few nanometer size quantum dots, they show the relaxation rates on an order of picosecond, which is the same order as in the bulk material. And actually, there was a paper in 2000 from Krauss in 2006, where he was showing that you go in smaller to the smaller sizes from, let's say, 5 nanometer to 4, 3, 2 nanometer. I think it was less selenide quantum dot, and you're getting even in decreasing. The relaxation becoming faster in 1, 2 nanometer quantum dots rather than 5, 6 nanometer quantum dots. So it's completely opposite behavior to what you can get from intuitive idea, right? And again, the reason is that your phonon couplings originated from a surface, which is very complicated, which is not just bulk crystalline surface as we have in the bulk materials, and all kind of defects, ligands contribute and increase the interaction with phonons, which results on a fast relaxation rates. So that's why just changing the size doesn't help to slow down the relaxation.
Okay, so in other words, you are creating some defect states inside the gap.
No, it's not necessarily inside the gap. Your gap can be open.
Okay.
So ligands passivate the surface, but they also have and the orbitals are delocalized to the ligands. So then when you excite the quantum dot, ligands also kind of involved, right? And their vibrations also contribute and coupled to the electronic levels of the quantum dot which you excite. And again, plus defects by itself, right? If you have a pure defect, then it might also contribute, and then the defect will be inside the gap. But even if you have no defects, in the sense that you have nice passivation through the ligands, so you will still have this contribution of ligands, which increase the relaxation rates, because they start coupled to this electronic degrees of freedom.
The spectrum of normal modes will be
Wide.
richer,
Wider.
will be covering more frequency ranges. So for almost any electronic transition, one could find vibrational frequency where energy will go to. One more speaker.
Yeah.
Just if after we're done.
But we're okay with that.
Yes.
It's only 1 hour.
Absolutely okay.
It's only 5:10. Any other questions? No? We're good?
John has another one.
John has one.
Oh, another question.
Okay, so kind of basing off what we were just talking about. So then, Levi, you're just looking at how when you change the chalcogenides, that's going to change the phonon modes more or less.
Yeah.
So how does the ratio of core to shell, like radius, how does that impact non-radiative rates?
So we didn't look at that because there's only 3 atomic layers that you can think about going from the center of mass out. And the first layer only has, I think, 8 atoms in it. And then the next layer has 8 again. And then the last, it has 8, then 16, I think, and then 52. So if you replace the second layer, you really only have 4 of each atom. So then I think you would get completely different results because you're no longer in like a core shell structure. You're like in a very local environment and then totally different around it. So then you would break the crystal lattice of the rock salt for the lead compared to the cadmium. So it would be very hard to see computationally different layers. And one of the papers that they use the effective mass, they can do it because their computational expense is much lower, and all they need to do is change like the lattice parameters from the core to the shell, but we can't really do that because we're doing atomistic simulations.
Then why not to do what they do? Why do we need atomistic simulations if they can go to the bigger quantum dots? Why we are so stupid?
Because they can't see the phonon modes.
They can actually introduce. I mean, it's a ground state calculations, but you can kind of use the same procedure for the dynamics, kind of through introducing normal modes. Technically, you can probably.
So what is missed in effective mass?
But what is really not working for us if we use effective mass?
What's not working for us?
Why
we don't
not doing effective mass? What is effective mass?
It's looking at you have your block function times spherical harmonics to
Why do you have spherical harmonics? How did you get spherical harmonics there?
No, sorry, not spherical harmonics. Particle in a spherical box.
Whatever.
Or spherical, what?
Bessel functions, spherical Bessel functions.
Yes.
It's like solution for the hydrogen atom. But
virtually
where
what you
get
do, what
so
do
you say
I get
spherical
what?
box, but how is the spherical, like, what is your spherical box in this case? You have a quantum
It
dot,
would
how are you
be-
getting spherical box?
Wouldn't it just be the size of your quantum dot?
Perfect. It means you really requiring that your quantum dot is a perfect sphere. Am I right?
Yes.
Because if you change in the
Yes.
shape, if it's oval, if it's having, I don't know,
Kings, steps.
something, then you have your
Defects.
solution will be not Bessel functions anymore, right? So it really depends on the shape of your container, of your box, of your well.
Yes.
But do we really believe that 1 nanometer, 2 nanometer quantum dots have a pure, nice spherical shape?
No, because you have different crystal lattice, crystal
Cuts.
planes in it.
Yeah, so,
So for rock salt, if you go to 68 of each cation and anion, you have a very, it's almost like a cube with the edges chopped off. So it's not spherical at all.
yeah. And plus the interface, right? So the interface between your core and shell also not really spherical, it has a atomistic structure,
Yes.
which might be
Which-
kind of changing the electronic levels.
Which one of the papers stipulated that for this slow relaxation, where you have this type of structure. Can you see my slide?
No.
No, you have to switch back.
I did.
Now we do, almost.
You can see it?
Now we do, yes, we do.
So this picture on the left, where you have like a stepwise potential, this is only seen when you have abrupt changes in your crystal lattice. So if your interface was not there, if the crystal parameters very quasi-continuously, you would not really see this nice stepwise potential. It would be more smooth, and the relaxation rates would not be the same as if you have a very strict domain where you have an interface.
What is the wave function for your particle in the box solution at the edge, at the border of the box? What does the wave function equals to at the edge?
So, an effective mass,
Yes.
I would assume it's equal to 0.
Yes, it is, but in a
In
real
this
system,
case,
in a real
it's not
system,
equal to 0.
yeah,
It
because you
tunnels
consider
out.
your box is having an infinitely long size of the potential, right?
Yes.
That's why the wave function equals to 0. But realistic systems, of course, have this potential being some finite energy.
Yes.
So you will have a
Yes.
tunneling through the barrier, and that's again will change the solution. Again, we will be having much more complicated solution, which analytically is not possible to do, and that's why any kind of surface effects, right, kind of squeezing linkage of the leaking of the wave function to the surface, to the ligands on the surface, and so on, right? All these effects are beyond the effective mass approximation, and with atomistic approach, I mean, with what we are doing, DFT-based approach, right? We of course can calculate all these details without any problems. Although we have to pay our price for being limited to very small systems.
Yeah. So if you can see my slide, for those of you that didn't quite understand what Svetlana was saying, if you look at panel C and you see the wave function, so if you look at the gray line and you see the black potential, the wave function exponentially dies in a sense, but it does not completely stop at the barrier. It kind of tunnels out. And that's the case for all of them. Does that make sense to everyone?
You should ask, lift hands if someone disagree.
Do you disagree, Dimitri?
He didn't he didn't push his hand, so he's fine. Are you?
Okay. Any other questions?
If there are no more questions to Levi, let's give him a round of applause. So we are not leaving yet now. There is one more element in today's program. Let's check if John and Levi can see. John and Levi, please confirm if you can see the content.
Yes.
Confirm.
So I kind of threw this together last night. And, it's not as in-depth as the last presentation. It's kind of a little more broad strokes. And I was feeling in a sort of creative mood, so just kind of bear with me on this. So the project I'm working on is inorganic light halide perovskite quantum dots. And then we're comparing an intrinsic dot, just a regular one compared to a dope one. And particularly, we are interested in their light emitting properties. So we're going to do a proper literature review on this, the situation. We got to start from the beginning. Can anybody think of the word "start" to describe light?
From the white screen.
Genesis. First 3 lines. And let there be light. I seriously kind of want to put that in the, like, whenever I first say light, just cite that in my sort of citation, see if literature review people actually see it.
Well, this is a great for presentation, right? But I think for your paper, probably not a good idea to
Yeah,
start with
I don't
these
want to poke
words.
the bear.
Because it's scientific paper, right?
Maybe title.
But to be light.
So we'll skip ahead a couple thousand years and look at perovskite quantum dots, and particularly we're gonna kind of walk you through the story of this photo stability of these materials. So I think there might have been some quantum dots, perovskite quantum dots made before this paper, but this is like the seminal paper for making perovskite quantum dots. I think it has over like 1,000 citations, which is a lot. So this is a group out of
Aaron, can I interrupt you and ask a linguistic question?
Mhm.
I was always hesitating to ask anyone and to go wiki dictionary. What the word, the last word of the title means and how to pronounce it correctly?
gamut.
Uh-huh. Any analogs?
I think it's spectrum.
Okay.
So I think that would be, that's the closest word I can think of anyway.
Okay. So if you see huh?
What are we trying to talk about?
The word gamut, what does it mean?
Isn't it like a?
I thought it was like a.
The common phrase like "run the gamut" is just like a wide variety.
Yeah, it's like a wide range.
Yeah.
So I think
No,
it's
that's gauntlet.
oh, yeah.
No, it's
People who use it for gamut too.
yeah.
Oh.
So the more we know.
Something to know.
So anyway, yeah, the impressive part with this is they can generate the entire color spectrum, which is handy for materials applications because, I don't know, white light is pleasant.
I missed it. They can generate different colors because of what?
Because so they change them primarily by changing the halide content in the perovskite crystals. So in like CAD, selenide, those are changed based on size. And there are some size effects here too, but they're second order compared to just changing the halide content. So it's easy to generate different colors, you just have to put in different chemicals. They're very bright. And then when they initially made them, you can get 70 to 90% quantum yields out of them, and people have improved those to basically perfect quantum yields, or 100% quantum yields out of them. And they're easy to make. You just basically mix chemicals together, heat them up, and the reaction goes in like 2 seconds. So it's very easy to do. You can do it pretty much in open atmosphere. But the cons that they found from this is that quantum yields decreases over time, and the red emitters aren't stable due to phase transition issues, but I won't really focus on that. And I highlighted the red parts because we're a photophysics group, so the quantum yield decrease over time is something interesting that we can look at. And a paper not too far after that one reviewed looked at the ligands that were used to passivate these quantum dots, because these quantum dots, they're passivated by ligands instead of an organic shell, like what Levi was talking about earlier. And then the two main ligands are oleic acid, which has a carboxylic linker group, and then an amine, or oleoamine, which has an amine ligand.
May I interrupt again? I probably missed it again. So your first paper, there was they're crystals or they're quantum dots?
Quantum dots, nanocrystals, they're synonyms.
Huh?
They're synonyms, like basically.
Well, I mean, they are not bulk materials. It's not like
Right.
big crystals. They're really nano-sized crystals.
Mhm.
What's the size of these guys?
10 nanometers.
Okay. Well.
I think they call them crystals because they're cubic, and they kind of look like salt crystals.
Mhm.
So, yeah, that's where nanocrystal.
And so when you go to the ligands, again, the story about ligands, you just need to passivate the surface.
Yes, because in this synthesis, they use ligands to solubilize everything, and then the ligands passivate the quantum dots to make them that small. Then it's found, and then this paper looked into the surface chemistry using NMR experiments I didn't really quite understand. But the summary from those experiments is that the ligand environment is very dynamic. So they found that ligands will pop off the surface of the nanocrystal, and then in order for them to be stable, you need like extra ligands within the solvation layer around it. So as soon as one pops off, we put one back in, which isn't very handy for if you're trying to do practical applications of them, because if you try to put them in solid state, you can't keep extra ligands around in the environment for it. So eventually the ligands are just going to keep popping off without being replaced, which will create surface states, which decreases the quantum yields over time.
Aaron,
Yes.
when you say stable, are you talking about emission being stable or the quantum dot being stable if you don't have ligands attached to the surface? Like, will it?
Photoemission stability.
Okay.
So stable quantum yields over. So you initially
Okay.
make them up a quantum yield of like 90%, and after 2 weeks or a month, they'll decrease to like 70%.
Okay.
This kind
I
of.
just wanted to make sure I knew what you were talking about.
Mm-hmm. Yep. So. Yeah, so that's kind of a big issue that needed to be resolved in these crystals, was just better passivating them.
So when you say ligands are pop out, they even pop out in the solid state? Well, you clearly have these processes in the solvent, but when you really dry it out, they still so flexible?
From what that's a good question. I think so, because I think people do make thin films out of them, and I think even over time those would kind of fizzle out.
Thin films by putting them in polymer matrix, or it just many quantum dots just deposited without anything.
Yeah, like a spin. So they just put a little drop of layer and then
Spin, so
spin
it's
it.
like no polymer matrix.
Or else they'd even like put like a little film in a centrifuge and try to catch particles like a fishing net.
Mm-hmm.
Pull them out, and then over time those would even degrade as well too, from what I remember.
And then covered by something.
I don't think. Well, they probably did, but I think even with that, because that would just prevent it from oxygen getting in. I guess I haven't looked at those papers in a while, so I could be misremembering, but those are good places to look at. So ligands. So just some. So the people want to improve the photostability of these materials so they can be used for practical applications. And then the three that I thought of last night that kind of pop out are, you can choose different passivation ligands, like up here. You can put on stronger binding ones to the surface that are, so ligands don't pop off. People use like thiol groups. And then recently, Kovalenko, they use Zwitter ions. I think that's how you pronounce them. So basically, you have a carboxyl and an amine on the same chain, and then those are more stable due to entropic effects.
So why there should be both kinds of ions?
Because perovskites in these they're ionic bonding, so they have charges. So you're gonna have different surface charges. So you're gonna have positive and negative. So you need.
But if it is stoichiometric crystal without any passivation, all charges are already balanced. Why ligands are needed, and why they need to be of this dual character?
Well, I guess to terminate surface charges.
But there is no if
Or surface
you
bonds.
okay.
I think.
So for surface bonds, and if you were watching something that what Levi and John were showing for cadmium selenium, there is often just one type of ligands. And here, papers that you were showing has two types of ligands all the time. And recent thing you've told about zwitterionic, there are both cationic and anionic species on the same chain. Why does both species are needed? What is special? Why it is not needed for cat selenium?
I guess cat selenium, they both have the same charges, so you only need one counter charge, or one type of counter charge. Where with these, you have lead is going to have 2+, so it's going to have a positive charge, and then the halide's going to have a negative charge. So for the negative charge, you need the amine to passivate it, and then for the lead, you need the carboxylic acid.
Question.
Yep.
In a lot of lead caucagenide or cadmium caucagenide quantum dots, you only passivate the cation, not the anion. Is passivating both ions in your perovskite important or not?
Yeah, because the conduction or the band edges, they're made up of the lead and the halide orbitals. So if you don't passivate one of them, you're going to get trap states easier to get into the band gap.
Yes, and for the quantum dots that I've worked on, are also the band edges are either the anion or cation, and you still only passivate one.
I guess I don't know.
Okay.
But this is known that it has to be on both cation and anion?
For them to be stable?
Well, I don't know. This is knowledge coming from just you were trying to do simulations and figure it out, or it's known experimentally, or maybe it's just from chemical point of view has to be this way.
I don't know, the chemical point of view makes sense to me, but I guess...
Like if you synthesize this emitting quantum dot and forget to put one of the ligands, will it
No,
emit?
but just a second. Is there a charge initially on your quantum dot before you put in ligands on the surface? Is it neutral, or it has already charge?
Should be neutral.
So
So
there
it's
is
neutral.
stoichiometry.
And then which ligands you again apply? You apply the charged ligands?
Yes.
Okay. So this is again the answer to Levi, that the way how he's using his ligands, they are not neutral ligands, they are already ionic ligands. And again, if he's putting only the negatively charged ligands, then on a neutral surface, right? So you are not balancing the charge. You need to have something to balance the charge.
Charge neutrality for the whole.
Yeah. In case of cat sulfide or whatever, the quantum dots, semiconducting quantum dots, which you are working, right? Again, if we're talking about neutral ligands such as amines, phosphine oxides, they're neutral, and even sialate, right? So that's why it does matter. And it looks like they bind stronger to the metal sides, not, well, because again, we understand due to the dipole-dipole interaction. So you have like nitrogen attached, of course, not to the sulfate, will be attaching to the cadmium, right? But if we have ionic ligands, right, we again have to balance it with going to the non-stoichiometric structure of quantum dots. And I think in his case, he just put in two types of ligands to balance the charge.
So this is a post-synthetic process, not a during synthetic.
Nope, these are used.
During.
Yeah, these are used like during the synthesis. So once they're made, these ligands are passivating the surface.
But then
This
the
ligands,
type
are they
of ligand.
solvent? Like, because when you do quantum dots, the ligands which you have on the surface, they're typically just coming from the solvent, like where your reaction is coming, wherever your solvent is. I mean, of course, you can make it differently, but this is the easiest way. You just organize the solvent, and wherever your solvent, this is your ligands on the surface.
These are a little different because.
So you really have to control it. You need to add this specific species when you do the reaction.
Then they use the ligands like to help solubilize the precursors too. So they're used for a couple of purposes during the synthesis.
But that's also the same thing for cadmium and lead quantum dots.
Not really the same. I mean, you can set up it in the same way, but technically,
Okay.
again, you just use amine. You can use amine solvent, and you will have your amine ligands on a surface. You don't need to add anything else to your solution.
Are we satisfied? Enough to keep going forward. So yeah, you can change out passivation ligands, which there's a lot of research going into that. You can also do inorganic core shelling, which I haven't really dug into that research too much, but it's out there and it's an option. But then there's also the option of doping with transition metals to get a stable emission out of perovskite quantum dots, and it's been a method that's been used for other sorts of quantum dot systems as well, basically, since people have been researching quantum dots. So it's one that people would naturally arise for perovskites. And so the first report I can find that looked at doping perovskites with transition metals was from the Klimov group at Los Alamos. And they found that they got a dual emission from the perovskite crystals after they doped them with manganese. So if you look at this panel here, the blue and the green correspond to emission from the regular quantum dot, and then the orange corresponds to emission from the transition metal. And then through their analysis, they characterized the emission from the Mn2 ion as a T1 to A1 transition, so it's basically a spin flip. So it starts in the excited state. So after photoexcitation, you have non-radiative relaxation from the conduction band of the perovskite to the Mn dopant. And then through a spin flip process, you can get a emission out of them.
So this analysis and assignment of the spectral terms is their educated guess, or it is some additional evidence? Where these terms are coming from?
So basically in all the papers I ever read, they say it's characteristic of the T1 to A1 transition for the emission that they see. So they see 600 nanometer orange emission, and then I guess that's characteristic of this spin flip transition from other systems.
How does the frequency of this transition depend on the environment? So there is a chlorine, bromine, iodine. Do this change of halide environment affects only the band gap of the host quantum dot, or it also affects crystal field splitting and color of this manganese emission?
I guess from just the ligand field theory that I went through, both chlorine, bromine, and iodine are weak field splitters, so they all have the same characteristics, so they all should have the same spin configuration for the ligand field, which is a high spin configuration because the ground state's a d5, or 5 upspins in the d orbitals. And I guess changing the halide would also change the kinetics for non-radiative relaxation and radiative relaxation, because changing the band gap, you change the energy difference between this level of the dopant and the band edge. So smaller energy gap, it's quicker transition to get there because you have less of a energy barrier to hop to that state.
And for iodine, it will not emit because the lowest excitation will be intrinsic, not on the manganese.
Yeah, so the idea is that non-radiative relaxation from this manganese state to this band edge is going to be quicker than this emission process, which is on the order of, I think it's milliseconds. So non-radiative relaxation is generally faster than millisecond. So and that's been shown in other systems too, where once you get to red emission of your intrinsic dot, you don't see emission from the manganese anymore, which I think I have a paper on that in here too, which we can get to eventually. So, we good with this? So that's just a broad overview of perovskite quantum dots and then doping of perovskite quantum dots. And so here are just a couple of theoretical papers or simulation papers on how to model the photophysics in these materials. So the first one comes from none other than two distinguished guests here, where they looked at 3 different relaxation processes in perovskite quantum dots. So they looked at multiple exciton generation, which is a little outside of my field for right now. So I'm mostly focusing on radiative and non-radiative relaxation for these systems. And yeah, are we the only group to model perovskite quantum dots?
Huh?
Like, are we the only group to model excitostate processes?
There is no doubt that even if there are no publications, there are many people who are trying to do it. And
But you're saying that you were not able to find any other publication on the excited state?
there are publications. Notre Dame, John,
Arkell?
yes,
Mm-hmm.
without Wiggins, big perovskite quantum dots.
Oh yeah, I remember that paper. It was something I thought of like last night, but I haven't delved too deeply into it. Because, well, it's pretty expensive, so it's kind of a hard thing to get your foot into the door with. So yeah, that's a paper on modeling perovskite quantum dots. And there was one paper I came across that was Yuri Danovsky. Is that how you pronounce his last name? Close enough. And where he modeled the luminescence of Mn dopants in Katz-Elnay quantum dots. But in this paper, he didn't actually do or compute radiative rates or non-radiative rates. He used some basically theorems to show that if you change the size of your Katz-Elnay quantum dot, that the Mn state is going to go away at some point, so you're not going to see emission above a certain diameter of the Katz-Elnay quantum dot. So that was like one of the big things that he looked at in that paper, and he also did some work looking at the ligand field splitting in these systems. And then this is really the only paper I've seen for people modeling radiative and or trying to model.
But which method he's using for calculating the spectra?
He didn't even do spectra.
Huh?
He didn't even do spectra.
Well, or electronic structure, whatever.
Oh, I think
He's using multi-reference approach, right?
No, I think he used DFT. No?
He's reducing the whole system to really kind of
Oh,
a
never
very
mind.
small complex,
He used
and was using something really more high level.
SAC-CI. I'm not sure what SAC is.
S, you can see it.
SAC.
SAC-CI. So yeah, it's a multi-reference approach.
See, it tells SAC-CI multi-configuration.
Multi-configuration, yeah, not multi-reference, multi-configuration. And I think in this paper he was showing that if you apply, if you apply like TDDFT, you will not see the right alignment of this D levels of the manganese or whatever his cobalt, whatever his doping. Manganese doping is. And if he's using his approach, then he's seeing it in the right position, in agreement with experimental.
He didn't see right energy levels?
Hmm?
He didn't see right splitting? of
Yeah,
the field?
actually, his model just gives you the splitting between the ground state and the first excited state. In the d orbitals, splitting between the orbitals in your, because he's considering just the, the impurity, the doping, manganese ligand, surrounded in a lattice of quantum dot, with the symmetry of the quantum dot lattice. So it's really like a very small complex. And then applying his method, and then he's seeing the splitting between the D levels of manganese versus, of course, whatever your levels are for this six atoms surrounding the manganese, right? Like you can take the smallest bonds which you have in your lattice. Well, create the lattice of Katz-Sulfide or whatever his quantum dot is. Is it lead-selenide or Katz-Sulfide?
Katz-Elnay.
Katz-Selenide. So it's a Wurtzite structure, so it means you will have 6 neighbors, right?
4.
No.
This one he has 4. Well, from the image it's 4.
Which side only has 4?
Oh, 4? Okay. I
It
thought
is,
it's
it is with
octahedral.
octahedral is with wet selenium octahedral.
That's rock salt.
Okay, whatever. So whatever the symmetry of this lattice, right? And then kind of really take just this small piece of your crystal, right? And the only thing which he was really looking on is splitting between d orbitals.
I guess I'll have to reread the paper because I guess that point didn't come across to me.
Well, he just gave many talks, which we were listening to. And I was actually a reviewer for at least for one of his papers. So I was really read it very detailed, in a lot of details, and asked a lot of questions to him. And then I guess at least one of this, I am not sure, was it this paper or some other? Yeah, probably this one looks very familiar in terms of figures.
You are the CAD solenoid expert. So, I guess one line that I came across when he was trying to describe, I don't know if the reviewers were just giving him a hard time about not computing oscillator strings, but he's saying that it was very difficult to compute oscillator strings for the DD transitions because they're so small. So it's basically impossible to calculate these. Well, I'm just gonna borrow a line from Dimitri and say, well, we attempted to do the impossible.
Well, I will tell you, the problem is with his approach again, what's really why this transition is optically active? Because it's hybridized with a lattice of your quantum dot. And then your transition ground state to this D transition becoming optically active because your ground state is coming from the quantum dot state. And there's also, if you're interested in this, you can find there's a papers of Katya Badaeva as the first author, and Xiaosong Li,
and
2008, 2007, 2009.
Several collaborative with Daniel Gamelin.
And they, well, I mean, I would say take the theoretical papers, and then, yeah, probably Gamelin is also...
Gamelin is more famous, and you can track his papers and then find his collaborators.
In experimental papers, they probably not provide really any kind of clear explanation what we're really doing, so there's really very minimal information from theory. But you can find the theoretical papers where they're also trying to do TD, DFT, and DFT calculations. They use, I think it's also cat sulfide quantum dots with manganese and cobalt dots.
They started with
zinc oxide.
Zinc oxide.
So zinc oxide quantum dot
because
with...
it has much bigger gap, and all transition metal doping states are kind of isolated inside the gap.
But the transition which you have, this optical transition, is really supposed to come in from your quantum dot to this D level of the doping. And of course, it will be optically active only if it's nicely hybridized, when it's not just localized on the margins, when it's hybridized with the entire thing. That kind of charge transfer character, right? And then this transition is bright.
So in these systems, it doesn't necessarily require spin flip. It just requires...
No, it will be spin flip.
Charge transfer or spin flip?
No. This transition is spin flip, but it will be kind of still will be seen anyway. Well, same as we see in the emission for phosphorescence emission from metal organic complexes, from a triplet emission, right? And it's not really pure triplet emission because it's really having a high hybridization with pi orbital. It's not just DD transition, right? It's a pi orbital D delocalized orbital.
Yeah, that's
and the more this delocalization with a pi transition, the brighter the state. Because you might have triplet being dark just because oscillator strengths of a triplet can be just dark, not because you flip in a spin from ground to the triplet. It might have just dark nature due to the dipole moment. Right? Well, anyway. But anyway, so since you mentioned this paper, probably look on the oldest papers for zinc oxide with the manganese and cobalt doping, where they use just DFT, and there were also some because I know these people, so there were some disagreement with experiment because really they were not able to get the right splitting between these d orbitals. But some reasonable kind of electronic structure calculations they provided, or at least some ideas is there. So you can take a look how they treat the spin and what kind of discussions they have there.
Makes sense. So then, yeah. Well, I was feeling in a creative mood. So once I saw that line about it being impossible, it's like, we'll try our best. So then, yeah, this is just a summary slide of, that was just an overview of the literature that I've kind of gone through. And through our work, what we plan to do is, for the doping systems, experimentally, it's like, I don't even know how you would figure out like the ligand field environment, whether there's ion teller occurring or not. So through our first principles calculations, we can give some insight into the ligand field that's occurring there, and that's really necessary to describe the radiative and non-radiative relaxations, because if we don't get the ligand field splitting right, we're not going to see the right optical transitions for the system too when we try to model it. So yeah, I guess that's all I have.
Okay, well, thank Aaron.
We lost Levi. Looks like he disconnected.
No, I'm here.
Oh, you're here.
It turns them dark for some
But
reason.
yeah, we don't see you. Okay.
Okay.
Any questions? No?
Any objections,
Disagreements?
criticisms, suggestions?
Or just interest? No?
So I'm still not 100% convinced why you need the charged ligands.
Why
Because
you need the charge ligands?
For
when you synthesize these perovskite materials, so is the charged ligands the only ligands that make the precursor soluble, or are they the best ones, or why can't you use like Lewis donating or accepting ligands to make your precursor soluble, and then you don't need to worry about charge ligands?
And you need to be able to convince your reviewers in the future. So right now Levi is your reviewer and he's not quite sure. So
I guess my initial response would be, I'm a material scientist at first glance, so the chemistry doesn't interest me as much. As soon as I make the nanocrystals, I want to move on.
No, this will
no.
This will not people buy, especially if you put it in.
That's just my initial gut reaction. But
I mean, this is you can try when you give a talk, right? But when you write in a paper and reviewers ask you questions,
it's something.
this will be not counted as an answer, right?
Mm-hmm. So yes.
Because again, don't forget, you're saying, oh, I'm a material scientist and I'm not interested in the chemistry, but your paper will be read by chemists as well, right? If you want to send it to the very focused journal, which will be really focused on the material science, then of course your citation index of this journal will be going down because it's so focused. So if you go into the high-ranked journals, means you're really addressing the broad auditorium, physicists, chemists, material scientists, maybe engineers, yes. Right? So that's why, yeah, you need to address chemistry and physics and everything what came to the mind of your reviewers.
So yes.
But these ligands, again, you were, like, my understanding is you have experience in really synthesizing these materials by yourself, right? Mm-hmm. And what exactly is it, like, you were using these ligands because it was done by someone else?
Yeah, that was
or you were really trying different ligands and this is only one which worked?
Straight from this paper, the original.
So you're just repeating exactly the same recipe as they have.
Mm-hmm.
And do they explain why they, what actually makes this choice of ligands? Like, why is this choosing these ligands?
Not really. So I think they use the carboxy. So they use the oleic acid to solubilize the lead precursor, and then they use.
And again, this is very similar to what people do in quantum dots, lead selenide, lead sulfide quantum dots. They start with the same precursors.
And then for the amine, they make you have to make a cesium oleate. So basically, there's a cesium atom that's ionically attracted to this part up here, and that's hot injected into the solubilized lead.
Okay, so then where's your halide coming in?
Halides
Well,
are
it's with
on
the
a,
lead.
halides are already
What?
in a,
It's a lead halide precursor.
Oh, okay.
but you also have halides in a crystal, right? For your quantum dot.
Mm-hmm. But he was wondering with
Like when it's growing, you need halides when they grow because they surround in your lead. Can you go back to your structure of the? Do you have actually the structure of the crystal? I mean, of the quantum dot crystal.
No, I just had a cartoon. But, it's
But it was in your post, I think, right?
yeah, it's cubic.
So you have the metal line which is surrounded by halides, right?
Mm-hmm.
And then kind of another lead ion, and this is your crystal structure. And you really cut this cubic from this crystal structure where leads is surrounded by halides. So halides are not ligands in this case. Halides really create the core of the quantum dot, lead perovskite quantum dot.
I may have an answer to convince Levi.
Try.
Yes, I'll try. So, Levi, you were presenting the core shell structures.
Correct.
And both core and shell are like donor and acceptor, oxidizing and reducing elements. In core, you have cadmium, selenium, and in the shell, you have whatever, zinc.
It's
sulfide.
opposite.
Huh?
Lead in the center, cadmium outside.
Okay, but you do have in both core and shell, you do have a pair of reducing and oxidizing elements, like metal and non-metal.
Yes. Correct.
But on the shell, the material gives larger gap,
Yes.
so that for electron and hole, it is not comfortable, not energetically favorable to go to the shell. They are enclosed into the core because the band gap at the core is lower.
So when you say that, are you meaning after non-radiative relaxation?
Yes.
Or
No, yes. So the
somewhat?
lowest
They see a dual emission. So emission from the core and the shell.
but the lowest excitation is at the core.
Yes.
Okay. So you agree on this summary of your work, of your literature.
Correct.
Now, let's consider core as the anions and cations from lead halide perovskite, and a shell consisting of anions and cations of some long organic molecules, which will give much bigger gap if they are able to participate in optics.
That's the same thing that is in most colloidal quantum dots. The ligand shell is optically active, but much outside of the range of visible light.
Yes, correct. And on one hand, on another hand, the ligands in the system that Aaron has presented try to mimic the symmetry of a crystal a little away from the crystal. So they keep the same coordination for each surface ion. On one hand,
So in other words,
yes,
you're saying that these ligands try to reduce the influence of the interface between the quantum dot and the ligands.
yes, and the rest of the world, of the environment
Yes.
around the quantum dot. Yes.
And that is not possible without charged ligands.
Correct.
Okay, then it makes sense.
Good.
Can I start my own applause?
No, any other questions?
No, maybe someone will.
Maybe people are just too shy to ask you a question. Give them time. No?
Maybe John wants to ask you something, or
He's a specialist in perovskites, right?
or maybe John
By the way,
is not happy how you didn't praise his contribution enough.
No, I thought he did just fine.
so
So
Ready to upload or not?
last chance.
What?
Daniel.
Oh, whoopsies.
I'm just gonna ask him to if he can send me the slides so I can look over those papers over spring break.
What?
I was gonna ask him to send me like the slides so I can look over the papers over spring break.
Okay. So it was a question.
Can you send slides?
I can.
So then we are ready, right?
Yes. Okay.
Yeah, but we had a lot of fun with your presentation. Thank you for trying to make it not very boring.
Great. So many thanks for participating. And if you are not traveling to the spring break, please consider to participate in the coming Tuesday meeting with conclusions. We are doing it with purpose so that when there will be deadline to have the whole paper and to submit it, we do not have too much pressure and hectic on one hand. And on another hand, if you are able to create your conclusions, it will be kind of your compass. Then you can wrap up the rest of the paper to keep only those statements that will later lead you to the conclusions. So
Why we can start with the abstract?
No.
Abstract is doing pretty much the same as the conclusion.
No, abstract is very limited by size, but in fact you can start with abstract. But let's try conclusion.
But I want just to mention that we have Levi who didn't send the figures yet, right? Levi?
Yeah?
You didn't send the figures so that everyone can make comments to your figures for your paper. Am I right?
Correct. I haven't had time to change them since you sent them to me. Your comments.
So now probably you can do it by this Tuesday. Now you've had enough time to do it, I hope.
Yeah. I think you sent it yesterday or the day before?
No, I sent it on Tuesday, last Tuesday.
I don't... okay, I'll look at the email.
I sent it like noon or something close to noon on Tuesday when we had a group meeting.
Okay.
Okay. Anything positive to finish on the positive note? Let's thank everyone once again for presenting and participating in the discussion.
Have a nice break. Those who are having